second video on hypothesis testing. It'll be a bit shorter than the first video, but it's going to serve as a good continuation as we move forward from this transition from descriptive statistics to inferential statistics. So in the previous video we learned about this new term, p-values, these probability values, and we know that they're based on the area underneath the distribution curve. And the larger that area, the larger the p-value, and the larger that area, the more likely we are to have gotten this extreme value, or one that's more extreme than the value that denotes the border of this, just by random chance. And so we're going to fail to reject the null hypothesis. But as this p-value, as the area under the curve decreases, we're going to gather more and more evidence against the null hypothesis. And so the smaller our p-value, the more likely we are to reject the null hypothesis. Now, where are we getting these p-values? Well, if we think back to the standard normal distribution, these are based on the area under the curve, and these are the probability values that are found within the center of the table here. For thinking about our t-distribution, these are the first row of our particular table. And so, whereas the standard normal distribution, we're calculating these values. For the t-distribution, we're actually predefining these values. But how do we determine which p-value to use when we are deciding if we should reject or fail to reject the null hypothesis? Well, this is a good question, and this lies into the fact of the basis of hypothesis testing. So we've got two possible outcomes here when we're thinking about this. We can either fail to reject the null hypothesis, or we can reject it, again, fitting back into probability theory and the binomial distribution. So we can put this into a table in which to help us decide how do we determine what our p-value should be to decide whether we should reject or fail to reject the null hypothesis. Well, in the real world, there's also two different situations. It could be that the null hypothesis is in fact true, or it could be that the null hypothesis is false. And at times, our decision will match up with the real world. And hopefully, this is what we're aiming for at all times in science. But there are situations in which maybe we reject the null hypothesis based on our data, but in the real world it's actually true. Or we fail to reject the null hypothesis, but in the real world it's actually false. Well, this first error is called a type 1 error, in which in the real world something is actually true, but our data is suggesting that it's not. And in the other situation, this is a type 2 error. And these are denoted based on these Greek letters of alpha and beta. Now, we can never avoid type 1 error, type 2 error fully. Those are always potentials, but our goal is to reduce those, because the only way to really eliminate those possibilities is to sample every single member of a population. As we talked about at the beginning of the course, it's very unrealistic and also oftentimes unethical when we're thinking about potentially removing animals from an ecosystem or causing some type of damage or threat to particular species. So, for this type 1 error, which is denoted as alpha, this is indicative of our level of significance. We've been talking about this a little bit throughout the class, significance levels and determining if something is statistically significant. And so we can actually set what this type 1 error rate is going to be. So in this particular case, we have alpha equal to 0.05, meaning that our significance level is 0.05, which means that the likelihood of rejecting the null hypothesis when it's true is 0.05, or it's 5%. So we're actually predefining what the likelihood is of making a type 1 error based on the significance level that we set. We can set alpha to equal 0.1, we can set alpha to equal 0.01, 0.00001. The lower the value of alpha, the lower the likelihood is of making a type 1 error. However, the lower alpha is, the more difficult it is to actually discern a difference between our data and what we're predicting, and in turn reject the null hypothesis, as we'll see as we move through this course. So this alpha value is our default p-value. It's the threshold in which we are going to decide whether there is some type of significant effect occurring or not, and whether we should reject the null hypothesis or not. As this again decreases, the threshold is going to decrease, and so we in turn need to find a value that is more and more extreme. For the type 2 error, this is based on the variability in our data. The failure to reject the null hypothesis when in fact it's false in the real world is based on how much variability we have in our particular data set, which in turn is also affected by our sample size. Now, we can't control how much variability we have in our data, but we can generally control our sample size. And as we've learned throughout the course thus far, the higher the sample size, the smaller the standard error, the smaller the confidence intervals, and in turn the smaller the type 2 error is going to be. And so this is something that we can control as well, and so making sure we have an adequate sample size is going to be valuable for us to not make this type 2 error, failing to reject the null hypothesis when in fact it's false. So we use this information in turn with our z-scores or our t-scores and their associated p-values to determine if we should reject or fail to reject the null hypothesis. And we'll talk about this in class more, but again, I encourage you to go to the text, specifically in this case section 6.3.2 for more information on this. So let's think about some examples in how we actually create these hypotheses. So say that TPWD is looking at the sex ratio of spotted sea trout. They want to know their status in Galveston Bay. Previous reports suggest that it's a 50-50 ratio of males to females, but when you're going out for your sampling, you're noticing most of these fish are females. So when we're thinking about the null and the alternative hypotheses, our null hypothesis, again, is going to be that which we're testing against. So even though you're noticing more female fish, the previous information is suggesting a 50-50 ratio. So the probability of selecting a female from the sample is going to be 50% for our null hypothesis, whereas for the alternative hypothesis, again, there's multiple versions of this. Maybe it's just the fact that we don't have a 50-50 ratio, but based on what our indications suggest is that our alternative hypothesis is that there's more female fish. So the proportion of female fish should be greater than 50%. Think about another example. Let's say that we have a faculty member in the department, and that person's studying bull shark movements, and he thinks that larger sharks are going to move greater distances. This makes sense. They're bigger. They can move more easily, and also maybe they need more food in which to meet their energetic needs. So when we're thinking about the null and alternative hypotheses, again, our null hypothesis is that which we're testing against. So even though Dr. Wells thinks that larger sharks are going to move more, his null hypothesis is going to be that all the sharks move the same. Again, this is our straw man. This is what we're testing against. His alternative hypothesis should be that as we increase age, those sharks are going to move more. And so age 0 sharks are going to move less than age 1 sharks. Those sharks are going to move less than age 2 sharks, and so on up the age structure of the population. Say that we have Dr. Rooker looking at the age structure of flounder, and he's thinking that these fish are on average 2 years of age. What are his null and alternative hypothesis? Well, again, in this particular case, his null hypothesis is that they're 2. This is what he's suspecting. But what he's testing against is the fact that he thinks that these fish are 2 years of age. And so his alternative hypothesis is that they're not 2 years. In this particular case, there's no evidence to suggest that he should suspect the alternative to be greater than or less than 2. One last example, Dr. Quigg is studying the effects of temperature on phytoplankton, and she's predicting that as temperatures get warmer, there's going to be more biomass. So her null hypothesis in this case, again, is what she's testing against. Even though she suspects temperature has an effect, her null hypothesis is that it doesn't matter whether the temperatures are warm or cold, there's going to be the same amount of biomass. Where in this particular case, the alternative hypothesis could be that they're not equivalent. More likely, it's that the biomass of phytoplankton when it's warm is going to be greater than the biomass of phytoplankton when it's cold. We'll spend a little bit of time working on developing our ability to generate known alternative hypotheses in class, but definitely work on practicing this and check out section 6.2 and 6.4. Next class, we're going to continue moving forward with hypothesis testing, and we're going to start looking at new statistical tests in which to determine if a particular distribution meets our expectations or not.